Hello all, welcome back to this series on Risc-free processor design using verilog. So in our previous sessions, we have completed the verilog code for B-type instructions, branch type instructions, and load upper immediate type instructions. So in LUI type instruction, there is a small modification. We have actually sign extended the immediate value, but we should not sign extend the immediate value. Instead, we should just add the remaining bits with 0. That's it. So instead of doing the sign extension, we have to fill all the remaining bits with 0. So I will show it here in the top module, a small modification. So in the load upper immediate value, instead of doing the sign extension, we should fill the vacant bits with 0. That's it. So in the load upper immediate type. Okay. So in this session, we will start with the jump instructions. So we have already seen in our theory sessions about jump instructions. That is, there are two types of instructions: jump and link instruction and jump and link register instruction. So jump and link register instruction is a small assignment for you. So I will explain jump and link instruction. So you can try jump and link register instruction on yourself. Okay. So in jump instructions, where jump instructions in RISC-V are used to alter the flow of execution by setting the program counter to a specific address. So these instructions can be unconditional jump or conditional, allowing the execution of a different code path based on the certain conditions, right? So we have seen all this in our theory sessions. So coming to this jump and link instruction, the opcode is 11041 and there is no function 3 and the format is J type. And coming to the description, so it basically jumps to a target address and stores the written address in RD. So it will jump to a target address and stores the written address in RD. So it is going to jump to a target address and it will store the written address in RD. Okay. RD is nothing but destination register. So coming to jump and link register, jump and link instruction. This is the opcode and the description. So these are the fields in JALR. So immediate field is 31 down to 20, RS119 down to 15, function 3, sorry, this is JALR. We want JAL. So this is JAL, immediate 31 down to 12, RD11 down to 7, opcode 6 down to 0. So immediate value. So to this immediate value, we will do the sign extension. Okay. And we will make it to 32 bit. And this is the destination register address is also stored in the instruction itself. Now we'll go into our code. So in our code, this is our top module as we are discussing from our previous sessions also. So from here, the instruction will be fetched from our instruction fetch unit, instruction memory with the help of instruction fetch unit. That is all we know. So from this instruction memory, we will get our instruction out and it will be given to our control unit. So what control unit will do? Based upon the field values, opcode value, it will decide what type of instruction it is. So coming to jump instruction, wait a minute. Yeah, so this is jump and link instruction. So here if the opcode is 11041, ALU control will be this value and jump is equal to 1. Here you can observe this output is equal to 1, jump is equal to 1 and remaining all other signals will be equal to made to 0. Okay, so this will be given to the output of this control unit. In the top module we will get these outputs. What outputs? Jump and ALU control. Okay, so this jump is further given to our DPU unit, data path unit, and it is also given to our instruction fetch unit. Okay, so the jump, which is the output of control unit, is given out to DPU unit as well as instruction fetch unit. Okay, so in the instruction fetch unit we can observe. So in the instruction fetch unit, one of the input is jump. Okay, so one of the input is jump. So it is basically a control signal for enabling the jump operation. So what happens in this case of jump operation? In the case of jump operation, program counter will be incremented by the immediate address jump. Okay, so the address which is provided in the jump instruction. So according to that address, the program counter will be incremented. Okay, so how we are calculating this immediate address underscore jump, which is calculated in the top module. So immediate value underscore jump, here we can observe, yeah, this one. So it is instruction out 31 down to 12, 20 bit instruction is there and it is sign extended. So the remaining 10 bits will be filled by the MSB, and this immediate value underscore jump is given to our instruction fetch unit. Okay, I hope it is clear. In the IFU unit, you can observe if jump PC is equal to PC plus immediate underscore address underscore jump. If jump is equal to 0, then program counter will increment normally. PC is equal to PC plus 4. Okay, you can observe here BEQ 0, BNEQ 0, BG is 0, BLT 0, and jump is equal to 0 only. PC will increment normally. If any of these branch control instruction or jump instruction is there, then program counter will increment according to the type of instruction, whether it is branch instruction or jump instruction. Accordingly, the program counter will increment its value. Now, so we have also seen that when there is a jump instruction, the value of the program counter should be stored, right? So how should we store that? So I've written the logic. So if reset, current program counter will be equal to 0. Else, if reset is equal to 0 and jump is equal to 0, current program counter will increment normally, PC plus 4, right? Current PC is equal to current PC plus 4. Here it should be current PC. Current PC is equal to current PC plus 4. Else, current PC will store the same value. Okay, so it will not increment. Else, if jump is equal to 1, then current PC will not at all increment. It will store the value. That is, before the jump instruction is given, what address is present, that address will be stored in the current PC, and it is given out of this module instruction fetch unit. So this current PC value is given to the top module. Again, here you can observe this is given to current top module, and from here this current PC is given to data path unit, DPU unit. This current PC value is given to DPU unit, and jump is also given to DPU unit. Okay. Now in this DPU unit, if we observe, where is this current PC? So yeah, this is current PC. So return address, basically we have written this as return, it is basically current PC. Okay, so this is return address I have written as the input. So this is nothing but the current PC which we are giving through the top module, this one, uh, this one. Okay, so this is the uh, return address. I have written it as return address. So this return address is given to our register file. Okay, this is given to our register file. Where this is coming from? This is coming from all the way from IFU unit, instruction fetch unit. Okay, so this is given to register file unit. So in the register file unit, you can observe this value. What is it here? It is nothing but, yeah, this one, return address. I think I have missed this. So input 31 down to 0, return address. So this address is stored into the memory location if it is jump instruction. So if jump is equal to 1, then the address which is given by the instruction fetch unit, that is a previous address, will be stored into the register file location. What is the address that is given by the immediate value, right rig number? Okay, so this is how we are going to store the previous address value, and we are going to the next address value. So I will draw it and show it for better understanding. So what is happening here in the case of jump instruction? So what is happening in the case of jump instruction? First, the instruction will be fetched out from instruction memory unit and it is given to top module. So from the top module, it is given to control unit. The instruction is given to the control unit. So in the control unit, accordingly, by seeing all the opcode field and everything, we will get our control signal jump is equal to 1. Okay, this control signal is given by our control unit. This signal is given to our top module. Okay, from this the top module, it will go to instruction fetch unit, IFU. So what happens in this IFU? By seeing this jump instruction, if jump, then program counter will be incremented by immediate value which is provided in the instruction itself. Okay, I've shown that, right, how to calculate that immediate value and how we are giving that. So accordingly, if jump instruction is there, program counter will increment by immediate value, and the previous value of the program counter is stored in the program counter itself. Current PC I have shown, right? So current PC will actually store the value. Current PC is equal to current PC only. So actually how we are storing is, so before jump instruction itself, before jump instruction, what happens? PC will be incremented by PC plus 4, and current PC will also be incremented by current PC plus 4. Current PC plus 4. So this two will work same. So it will also increment from 0, 4 like that, and current PC will also be incremented from 0, 4 like that. So what happens if jump is there? Program counter will increment by the immediate value, but current PC will store the default, its previous value. Okay, that's how we are storing the previous value of the program counter, right? Now, this current PC value is given from IFU. It is given out from the IFU and it is given to the top model, and from the top model it is given to the DPU unit, and in the DPU unit it is given to the register file unit, and in this register file unit this current PC value will be stored. This current PC value is stored. So this is how we are incrementing the program counter by the immediate value, and we are storing the previous program counter value in the register file. Okay, so this is how we are going to execute jump instruction. So what is your task is to implement JALR instruction, jump and link register instruction. Once try this executing this instruction. Okay, so that's all for this session. Thank you.